So it's live, like it's going now. Yeah, got a game inside this. Yeah. Ian, look at Melanie. Look at John. Ian. Ian. It's John.
Man, I'm trying to set up. Trying to add myself to the room.
Ian. Look, Ian. It's Darth Vader.
That was me.
Really?
Keep it safe. That was me.
Oh. Just like crap out.
No, I don't know. Yeah. Yeah. It's gonna be like either you get fired or I don't even. Either Jaime gets fired or.
What?
He's not gonna get fired.
I'm not gonna go high.
Zero. You know him.
Who's seen fucking psycho? Yeah. Marcus.
Video clips and live streams. It's weird.
It is weird.
Like a South.
Wait, I'm not getting fired.
But it wasn't live stream yet.
I might get kicked off.
Why?
Because my dad thinks I'm not doing my college apps because of this shit.
You should do both.
Why is it mirrored?
Maybe you're not the only one seeing the
Sometimes it doesn't.
Let's go to the first.
Wait, one.
Don't do it. Do it. Do it. Did you say do it?
No, I said don't do it.
I said do it.
Okay. Okay, hey guys, so we're going to be starting our presentations. My name is Jan, and I'm the president of the robotics team, Steelhawks at Townsend Harris. Neil, Vijay is our safety captain, and Neil is our vice president, and we will be giving presentations on safety, drivetrain, and programming.
Does that work? Yeah, it's working. Okay. So first of all, thank you guys for coming to our school and our presentations. We really appreciate it. My name is Vijay, like Dan said, and I will be presenting safety. So safety is an important part of the first competition. Without safety is an important part of robotics and life. So safety involves whether it's wearing goggles, learning the proper techniques to use a tool, or whether it's crossing the street. Being safe is extremely important throughout everything you do. But sometimes safety is easier said than done. Throughout my time on the robotics team, I noticed that most people follow the most obvious rules because they prevent the most obvious dangers. But people usually forget the simple stuff, like wearing your goggles or wearing your gloves. So, and people make mistakes sometimes, and most of the time it's the simple rules. So, goggles are important. There are practically no cons to wearing goggles. They're stylish, they're hip, they're cool, and they protect you from anything that's airborne. So, keep your goggles on. Another thing I noticed is that sometimes people don't have their hair back when they have long hair. So if you have long hair, you wouldn't want it to get caught in any of the robot's moving parts. And you guys should bring hair ties and tie your hair back, or I will make you wear rubber bands, which aren't that stylish. So please wear hair ties. Also, another important safety rule is wearing closed-toed shoes. If you have open-toed shoes, you will not be allowed to work on the robot or be in the pit area at all. And I will also make you wear Crocs for the rest of your lives. So please bring closed-toed shoes. And part of being a safety captain is knowing how to take care of wounds. So we have a first aid kit with various items. We have gauze pads, just in case you have a cut to stem the bleed. We have ice packs in case you get hit with something and you have swelling. We have gloves, alcohol pads, bandages, but we do not have prosthetics. So please don't amputate any limbs, because that would be really, really bad. Now, the drill about drills. When carrying a drill, keep the drill in the lock position and use both hands to carry it, one on the handle and the other one on the arm. Hold the drill with both hands when you're using it. Hold it by the handle and by the arm as well. And always put the drill lying down instead of standing up. If you put the drill standing up, it's more likely to fall and hurt somebody. Now, soldering. Always wear face protection and use a mask. Solder in well-ventilated areas. Never touch the iron because it's hot and you could burn yourselves. Always keep it in its holder when you're not using it, because that would prevent it from falling and hurting somebody else. Also, wash your hands after soldering and use lead-free solder. Now, with great power comes with great responsibility. When using a power source, using an electrical power source, always power down the robot by opening the main circuit breaker. This you should do when people are either working on the robot or nobody is in the pit. This would prevent anybody from accidentally getting hurt by the robot, just in case it misfires. Also, if you have any pneumatics on your robot, be sure to release all the pressure. That would decrease the chances of anything like firing and hitting somebody. That actually happened to Marcus last year during the competition. Robot shot his catapult and hit him right in the head. Okay, so batteries are life. So you want to take good care of your batteries, and do not use any damaged batteries, because if you use any damaged batteries, you have a chance of it exploding. And if you have a leak in the battery, do not touch the leak. We have to use baking soda to neutralize the acid, and we have to wear acid-resistant rubber gloves to dispose of the battery. We have to treat the battery as a hazardous item, so we have to know how to take care of that. Also, if skin comes into contact with the acid, you have to pour large volumes of water and seek immediate medical attention, because sulfuric acid burns on contact. Now, if anybody is injured, you have to tell a mentor, send the injured person to the EMT, and fill out a medical incident report form. So that's the standard procedure if anyone gets injured, and it's important to follow that, because you want to take care of the person immediately to prevent any other damage that might occur. Now, when lifting the robot, always use your legs to lift the robot and not your back. Two people should always lift together, and use gloves when lifting the robot. The most important rule in safety is use your common sense. Common sense is like your best friend for life. Common sense will keep you safe most of the time, and always be aware, be rational, and don't be immature. Oh God, it's Jake. Anybody saw? Jake wants to. I want to play a game. People are in unsafe situations. Their lives are in your hands. You have 1 minute to name 3 unsafe things and describe how to make it safe in order to save each person. Okay, guys, we gotta save all these people. Alright, guys, name 3 things. 3 unsafe things. Anybody raise their hands? Yeah. Okay, that's 1. Huh? That's 2. One more, yeah. Alright. That guy is safe. Good job. Now this one. Marcus? Okay, that's right. Good job. Anybody else? Anybody? Come on, we need 2 more things. Or else it's gonna... Yeah. Hmm? Yeah, that's another thing. Okay, one more. Got like 30 seconds left. Come on. Marcus again. Okay, that's... Alright. He's safe now. What about this guy? Yeah. Okay, alright. Two more. Anybody? Two more. This guy's life is on the line. Come on. Mitchell. It's not, so how would you fix it? Alright. Yeah. See? Everybody forgets the simplest rules. Now this... Oh. Yeah. Okay, alright. That's true. Yeah, Victoria. Alright, one more? Yeah. Okay. This guy's safe now. Oh. Yeah. It's not a drill.
She is, but she's not holding one arm and one thumb.
Well, it's not a drill. It's a... Okay. Yeah. Okay. Yeah.
There's no measure or any safety cap for any of that.
Okay.
A supervision.
I mean, what if this thing starts moving? Come on, guys. Yeah, Marcus. Okay, her hair. Yeah. Javaria. There you go. Extra points for you. Alright, now what about this guy? Victoria. Okay. Yeah. Okay.
She's not holding with both hands.
Good job. Okay. This guy's safe. What about this? What's on? Come on, all these people's lives are on the line. Huh? They're sawing. Anybody? Come on. Yeah. Common sense is important. See? And Victoria. Okay. What else? There's the biggest thing here. About fire. There's actually a lot of people on the log. If all their weight could make the log collapse and cause serious damage to everybody there. What about? Oh, we have to save the former captain. Okay. What else? Marcus. Okay. What else? No. Somebody said no seatbelt. What? One more. Victoria. See? All these things are important. Also, he's sitting on the robot itself, which is terrible. See, you can break the robot, and what if he falls off? What's gonna happen then, right? Alright. That's it. Let me just have a little video for you, just yeah. Let's see. Anybody have any questions on safety or whatever? Nobody? Yeah. Which situation? That one?
Yeah.
I mean, well,
Your face.
I mean, not really. It didn't hurt that much to use a mask. A mask is like kind of overdoing it in that situation. What else? Anybody else? Okay, so being a safety captain inside the pit, you always have to be alert all the time, and you have to always know what everybody else is doing. You have to be aware of all your surroundings, and everybody has to be aware of all their surroundings. But especially the safety captain, we have to keep a keen eye on everything that's going on. Make sure that everybody's following safety protocols, and also following doing whatever they have to do in the correct way. Mr. Raymond?
See at the competition, there's a bunch of teams out there that have different ways of getting received from rocks. But it's still lots of
Okay, so during the competition, we had little safety kits that we gave out to different teams, and we also had these little papers that had miscellaneous safety tips on it, and we gave those out. They had little drawings on it, and it was like spreading the word of safety around. Some of our rules in the pits are we have always wear your goggles in the pit area, always wear gloves when lifting the robot, always wear gloves when you're working on electrical work, and be courteous, and always keep a distance from the robot when it's moving. Also, be aware of all your surroundings, and you should be fine. Any more questions? Okay, so I have two trainees with me. I have Justin and Courtney. I'm teaching them to become safety captain when I leave. They're coming on really well. They're actually really good. I like working with them. Well, when I'm training new people, I usually give them an overview of the general rules, and then I see what they're able to do on their own. And then when I see them do something I wouldn't say wrong, but when they don't notice things, I will just point it out to them and tell them to go fix it. Any more questions? Yeah.
It's two. What is the pit and how small or wide is the pit?
Okay, so our pit area is like a 10 by 10 foot area where everybody kind of works on the robot itself, and the pit area in general is like all the pits of all the different teams combined. So yeah, you need to wear goggles whether you're in your team's pit or just in the general area of all the pits. No problem. Any more questions? All right, thank you.
Okay, so we're gonna have a 10-minute break right now. So you guys can take out.
I'll see you later. So call me at least half an hour. Okay? Sorry, I'm here for you.
Good job anyway. Chris, welcome to my kids. Call is not done. The mic was not on.
No, it was not. It was just. No, stop.
You're on the bus.
Okay, hi, my name is Jan. I'm the president of the robotics team here at Townsend Harris, and I'm going to be telling you guys about drivetrains. Okay, so what is a drivetrain? So the drivetrain is basically the mobility of your robot. It's how we move during the game, and it's very important. But what do we want from a drivetrain? What we want from a drivetrain starts first with speed. You want to be a fast robot to be a competitive robot. But with speed, you also need pushing force. And pushing force is to get out of sticky situations like T-bones. And with that, you also need agility. So we need speed, pushing force, and agility to have a very good drivetrain and a competitive one, a competitive robot. And what are we given by FRC? We're given the Kitbot by FRC, and what does the Kitbot give us? So the basic Kitbot, it is a tank drive, so it has, it's a tank drive. And with this tank drive, we have two sims. We have a Tough Box Mini, which is the gearbox. We have 6 4-inch rubber tread wheels, and we will get to the speed later. I'll show you how to figure that out. So first we start with power, and our power is given to us by sims. So these are the sim specs. We have the free speed, which is the rotations per minute. It's basically how fast the motor allows you to turn the wheel. And we have the stall torque, which is the rotational force, So basically we learn from this is that more sims equal more power. Next we have the reduction. So if I were to stick a sim straight onto a wheel, it would rotate 5,310 times per minute. And that is too much, and it would be unsafe on the field, and it wouldn't really be able, you wouldn't be able to drive with it. So what we need is a gearbox, and the gearbox that's given is the Tough Box Mini. So we're going to talk about gear ratios. Now in the Tough Box Mini, we have a 14-tooth gear, 50-tooth, 19-tooth, and 45-tooth. And the gears have these teeth to pretty much give it an identity, and it makes sure that they work together to create a different gear ratio that states how fast your wheel will be moving. So to figure out the gear ratio, we need to separate it into different parts. We have the first stage, which is in orange, and we have the second stage, which is in purple. So with these stages, we have to divide the number of teeth. With the driven gear, which is attached to a motor, with the driving gear, and then the driven gear, which is 50 teeth. So it would be 50 divided by 14. First stage, which is 50 divided by 14, and then the second stage, which is 45 divided by 19. So the reason that we're dividing these is because we have to divide the driven gear by the driving gear. So the driving gear here is attached to a motor, which drives this gear, and then this gear drives the 19 one. So now the 19 is a driving gear, which is then driving the 45 teeth gear. Are we getting that? Okay. So this is only the different gear ratios for each separate part of the gearbox. Now we need to bring it together to get the overall gear ratio. So to do that, we multiply the stages. So we multiply 50 divided by 14 times 45 divided by 19 to get an overall gear ratio of 8.45 to 1. Now what does this 8.45 to 1 gear ratio tell us? First, it tells us how fast our wheels are going to be moving. To figure that out, all you have to do is divide the rotations per minute from your motor. You divide it by the gear ratio that you have, and you would get the rotations per minute of your wheel. Next, we get the torque that is given to the wheel. And to do that, you would divide the stall torque given by the motor, multiplied by the gear ratio that you have, and you would get the torque of the wheels. So with this, we see that there's a give and take situation. When you want more speed, you have to go for a lower gear ratio, and when you want more pushing force or torque, you would need a higher gear ratio. So the rotations per minute really helps us in figuring out the speed of your robot. So what we're given is the RPM, which is the rotations per minute. And this is the angular speed, so it's how fast it's rotating. And we need to change that into a linear, linear velocity. So we're given angular velocity, and we need to change it to linear velocity. And velocity is just speed. So through that, we use this formula, which is the linear velocity equals the angular velocity times pi and times d, which is the diameter of your wheel. So with that, we go into wheels. The wheels that we're using in the Kitbot is 6 4-inch rubber tread wheels. Now, why are we talking about wheels? Why would that be important in a drivetrain? Well, pretty much it affects the speed and torque that we're given. So like I was saying before, the linear velocity is affected by the size of your wheels. It's the diameter and the diameter that affects it the most. And it also affects the pushing force by the same reason. It's the diameter that affects it. It also creates frictional force. So while we're driving, there is a force that is fighting against us, so we don't want to drive. But we have to beat that force to actually drive. The size and material of your wheels matter in your drivetrain. So now we're going to talk about forces that are happening inside this drivetrain. So that's a nice wheel on a carpet. And we have the gravitational force, which is basically the weight of your robot. And to find that, it's just mass times gravity, and the gravity is a constant, which is 9.81 meters per second squared. And this force is going down because gravity is pulling us down. Next, you have the normal force, which is basically support force. It's the force that we are on, it's pushing back on us. So the normal force is going towards gravity. In this sense, it's acting against, they're both the same because we're not having a wheel that's flying up in the air. They're both equal, so they're the same here. Next, we have the frictional force, which I like to call the fighting force in this situation. And to get the fighting force, you would need the friction coefficient, which is also known as mu, and you can find the friction coefficient on AndyMark. They tell you the coefficients of your wheels on carpet, because we use those. And that's the force that's actually allowing us to drive in this situation. And next we just have the force that we're given to the wheel, which is going backwards. So the frictional force is making us drive. Okay. So we're seeing with the Kitbot, it's either a speed or pushing force situation. But why not both? I present to you shifters, the way that you can get both of them in a very simple and easy way to attach it to your Kitbot. And what we used was the 3-sim ball shifter. What's a shifter? Well, basically, it's a shifting gearbox. And what happens in this situation is we both have a low gear and a high gear in this gearbox. So we both get speed and the pushing ability. But how do we do that? So this is the gearbox that we were given by first, the Tough Box Mini. It has the 14, 50, 19, and 45. Simple, normal, you guys know how to do this. Now we're just going to add another gear, no big deal, don't worry about it. We have the 50, 12, 34, another 34, and a 50, and they're still separated in their 2 stages. So first, we have to engage these gear ratios. And to engage these gear ratios, we have 2 main methods. We have the ball shifter, which engages it by using pneumatics to put balls into those little holes around the side, and it gauges the gear. And then we have the dog gear, which does the same thing. It engages it, but in a weirder way, I would say. It does it more, it has to fit into those specific holes that were made. Now to make this at least a little bit less frightening, replace it with an actual dog. Okay, so the dog gear would actually be between these 2 gears. So we're shifting between the 34 and the 50. So when it is engaged with the 34 gear, we are only having the first set working. And when it's only on one stage, we make the 50 tooth an idler gear. So right now, the 50 tooth doesn't matter. It's going straight from 12 to 34. So it's only one stage. So what we would do is just divide 34 and 12, and you would get 2.83 as the high gear. Next, when it's engaged with the 50 tooth, we're going to begin creating a gear train again, which is just 2 stages coming together. So we have the first stage, which is 50 divided by 12, and the second stage, which is 50 divided by 34. So right now, the 34 in the corner is just hanging out, pretty much. And we got a low gear ratio of 6.13. So now we have to see what this actually accomplished. We have a tank drive, and we have a tank drive with a shifter on it. With the tank drive, we have 2 sims, a Tough Box Mini, 6.4-inch rubber tread wheels, and 8.45 gear ratio, which gives us a speed of 8.5 feet per second. And this is based on the motors giving us 4,100 RPM, because motors don't give us all of their power all the time. And with the tank drive shifter, we have 6 sims, 3 sim ball shifter as our gearbox, 6.4-inch rubber tread wheels, both a high gear and a low gear ratio. So we have 7.08 to 1 for our high gear and 26.04 to 1 with our low gear, giving us a speed of 10.1 feet per second. So as you can see, it gives us more speed, and it also gives us the ability to push if we need to. So we have videos from the summer that we tried using shifting gearboxes. Let me show you the pushing part of it. So as a reference, I'm like 90 pounds, just saying. And it's going to be pushing me very easily, actually. Never mind, sorry. Oh, wheels like 120. Yeah. Yeah.
Huh? No, it's all video. Yeah, I wish.
I could just get our attention here. Thanks.
What was the pneumatics working? So which one was fast? Yes.
If we could line up.
Vijay.
So I was like, so at like 10 o'clock, like, Neil, is it 10 o'clock or 11 o'clock? And I was like, oh, if it's 10 o'clock, did you guys already start? He's like, no. And I was like, I'll be there in like 45
Say hi.
minutes. Hi. Are you live streaming?
Yeah.
Can you delete that part?
Oh, I got to turn off the.
This is
Could you film for me?
so this actually
Point this at the robot. Right now it's live streaming. I'm gonna fail though. Get. Guess we're small.
Very slow.
Would you hold the tablet while I go switch to the live stream? Right now it's streaming. The Wi-Fi breaks it off and
Keep the hands away because this thing will break their bone. Yeah, like that. Yeah, that thing will snap your hand. Especially when you have to keep dragging, they don't know better. Even when you kids are driving, so just be careful, that's all I'm saying.
What time will your next presentation start? 12 what? Lunch break.
I think this would stay for the
Jan, when does your next presentation start? When does the next presentation start? 10 minutes? We got lunch.
Yeah, I know. I saw it.
Wait, Ian.
We were actually over in Toronto. Yeah. And what was really funny is they went to weigh in the tanks. And so we drained the tank. I don't know how much weight air really is. Compressed air has quite a bit.
So, on the last one, you don't need to talk.
Ian.
What you call me?
It's like his own thing.
Thank you. On standby.
Yeah. Not yet. Stop, Jamari. I'm waiting for it to go on standby. You're having the greatest like a type. It doesn't matter as long as it's not jelly.
Oh, I know I'm fine
Yeah. Ian, do you want to turn it off? Stop.
I don't know, well, the screen is
direction now. And likewise, on the other side, I feed the same value to the left motors. Everyone with me so far? Cool. So that means that my robot goes full forward. The code to do that is actually quite simple. So earlier we had our method of controlling it where we just control one side with one joystick and the other side with another joystick, which is just like this. Now all the gray stuff we've already written, things I'm adding new are black. So all of these new talon declarations, I have to tell the robot where my talons are plugged in. And then I just set it to the same value. So if I run that code, here's my code for a drivetrain with 4 sims. There we go. So here I've set up my talons, and here I'm setting them all to one joystick. Does anyone know why I have the negative sign in front of one joystick? Just curious. Yeah. Okay, but why would I want to move it backwards? Anyone else? All right. Yes, Wayne. Right, exactly. So on a drivetrain, my motors aren't necessarily facing the same direction, right? So I have 2 motors facing the right and 2 motors facing the left. I have to reverse the direction they're going to keep going forward. So there it was. Oh, nope. And if I run that code, now I have 4 sims, and you're going to notice a little bit of a speed difference. So I'm actually facing the wrong direction right now. Let me go backwards at full speed. And full forward. And if I step it at a 0.5, up there it goes. At a 0.5 second rate. Now if I step it, there we go. If I step it forwards, it's going to go significantly faster than the other drivetrain, and I can turn faster than the other drivetrain for reasons that Gannon explains. So control of a 4-sim drivetrain is not that different from control of a 2-sim drivetrain. You just add 2 more sims, and you negate the respective sides. Yeah. Yeah, you have more power. This simulator naturally can't simulate all the things like traction and the weight of the robot. It's mainly just simulating the direction, so you might not get all of the realistic controls. This year, they're actually possibly introducing something called Gazebo, which could simulate a robot more accurately, but nothing on that yet. So here, oh, no, video doesn't play, whatever. Well, anyways, this is Andy Mark's AM1 for you, the drivetrain that we commonly use, and you would be able to control it using just those 4 lines of code we just added. This is commonly called tank drive, because much like a tank, you control one side and the other side independently. Each joystick controls a different side of the drivetrain. However, yeah, so if I had a gamepad here, those of you who are driving the shifting drivetrain outside saw that I could control each side with one joystick. So each joystick on this Logitech controller corresponds to a separate joystick in our previous diagram. So if I wanted to move forward, I would move both joysticks forward. If I wanted to reverse, I would move both joysticks in reverse. If I wanted to turn, I would move one joystick to forwards and the other backwards, and vice versa. Now let's say I only have one joystick, which is what the large red robot Tomahawk was doing. Now I want to control my robot so that I'm going forward when the joystick goes forward, turns right when the joystick swings to the right, goes backward when the joystick goes back, and turns left when the joystick is swung to the left. This is commonly called arcade drive because, somewhat like an arcade machine, you use a single joystick on there to control the direction of the robot rather than 2. So here's a top-down view of that joystick where I have a forward y-axis and a horizontal x-axis. I can label these axes as the movement and rotation axes. So for the y-axis, I want to control how fast the robot is moving forwards and backwards. I want to see how quickly it's moving in that direction. And for rotation, I move it left and right. So if I start out with my joystick in the little green nub position in the center, move and rotate both equals 0. This is just a coordinate Cartesian plane. If I move my joystick full forward, move now equals 1, rotate equals 0. If I move my joystick all the way to the back, move equals -1, rotate equals 0, and so on and so forth, right? If I move my joystick all the way to the right, rotate is 1, move is 0, and all the way to the left, move is 0, and rotate is -1. This is the basis for our next arcade drive algorithm. So now what happens if I have my joystick in an intermediate position like the top right? Now move is at its full value, 1, and rotate is at its full value, also 1. If I move it to the back, move is 1 and rotate is -1, and so on and so forth. All clear, right? Cool. So this actually lets us simulate a very simple algorithm, which is the left side of the drivetrain should be the value of move plus rotate, and the right value should be move minus rotate. And if we look in the WPILib source code, it's actually quite similar. They just have a few more exceptions to handle like a joystick going haywire. So if I had my joystick all the way to the right, move would equal 0, rotate would equal 1. Now my left side of the drivetrain has equal to 1, and right equals 0 minus 1, so negative 1. Now I'm turning in place. So we can also implement this code in our Python script. So here I have arcade in two-wheel drive, implementing the algorithm I just saw. And you can ignore all the self things. That's just some Python syntax for object-oriented programming for those of you who are familiar with it. But everything else is just I'm saying set the left motor to the y-axis, or move, plus the rotation axis, which is x, and set the right motor to the y-axis minus x, which is exactly what we just saw. If I run that code, now what I should have is I'm only controlling with one stick now, right? So I can totally ignore stick 2. I'm going to step it in 0.5 second increments. So now it's not doing anything, right? So if I set full forward on y, full forward on y, it should move forward. If I set full forward on x, so now we're at move equals 1, rotate equals 1, I turn. And I turn in an arc just like that. And if I set x equals negative 1, I turn in the other direction. This is the control algorithm which lies at the basis of most FRC robots. So if I just wanted to control a robot with a single joystick, I have to write only 2 lines of code, basically. Right. Now let's expand this to support more talons. I should not say that. Okay. WPILib has utilities built in to support different drivetrains. We don't have to write all these algorithms ourselves. So the background is actually 190, WPI's own team. The 2 functions included are arcade drive and tank drive. So if I wanted to perform this behavior of arcade drive, I could just call WPILib arcade drive. So here's my example of arcade drive. Okay. This is WPILib's arcade drive system. So now, instead of saying, like I had before, let's say, beforehand I was declaring each left motor and each right motor. I still want to do that. I still have to feed those values into WPILib, but now I'm going to define something called robot_drive, which could be any title. I could call it like, Vijay drive or whatever. So I could put in the left motor and the right motor, and WPILib's robot drive utility will automatically spit out the values I need to drive a robot. So I'm going to feed in the stick, the joystick that I'm using to drive the robot, and now robot drive is going to handle everything for me. So I'm going to run robot drive now. And if I run that and I step it in 0.5 second increments just to show you what's happening until I operated, and now we get full forward, full backward, an X rotation to the right, and an X rotation to the left, because I'm going backwards. Right, there we go. So all pretty simple so far. WPILib emulates the same behavior I just showed you in the 2-line algorithm with its own class. And I can do the same with tank drive. So here's our example from before with tank drive going on. We have 4 talons being fed into the values of 2 joysticks. So I have the left stick giving the left motor's values and the right stick giving the right motor's values. This can get very long and very complex quickly enough, so we're going to just replace that with WPILib functions. So now instead of saying set all 4 motors into whatever sticks are saying, just give it WPILib robot drive tank drive left stick and right stick. And now I can control the robot. I can control the robot with just that one line. So here's my example for. There we go. Right. So there's my 4 motors being defined. There we go. There's my 4 motors being defined. You have the left, right, right. Sorry, left, rear, right, rear, left front, and the right front. And you can control the robot just using tank drive like that. So if I run that code, I can now emulate the behavior of my drivetrain, which was in tank drive. Oh, no, not that one. Tank forward drive. And if I run this code in 0.5 second increments, and I put it in teleoperated mode, I can now put each joystick controlling one side of the drivetrain. So stick 1 controls the left side, and stick 2 controls the right. I'm going to go in 0.5 second increments, and I go full forward. I can go turn to the left. very quickly, or actually I can't even tell what that is, to the right, sorry. And vice versa, each joystick controls one side of the drivetrain. So this is the same behavior we had before with our own algorithm, right? Let's say you now want to take this to the next level. Team 254, world champions this year, uses a system they call Cheesy Drive because they are Team Cheesy Poofs. Cheesy Drive is a system that's also been used by teams like 971, who are endemic to California. And that system can be very effective. So here's 971 in a match of Cheesy Champs. And I want you to see how they're driving. With that buffer. So Team 971 is running a, octagonal drivetrain this year. So they had 6 wheels just like everybody else, but their control was very different. And it's also buffering badly. How sad. That's terrible. But you can kind of see Team 971 is that one with the spike things on top. And I want you to see how they maneuver around their Defender 604. Right. So that little, just a very small area they turn in and they move effectively around their opponent is because they have an effective control system, which is... Oh yeah, so other teams will also use other alternatives. So naturally, I don't have time or the resources right now to explain every single team's drive algorithm, but Team 33, for example, uses something they call Culver Drive. It's named after a guy named Brian Culver, where they use a gamepad. And one of the traditional problems with a gamepad is if you want to move a drivetrain, you can really only go full forward and full backward. It's really hard to get an intermediate value, right? Because it's just a small range of motion. So what they do is they interpolate and they give you one joystick controls the direction instead, and one joystick controls full forward and full backward. So now you can control your turning more precisely. And for those of you who are around in this season and you were watching the Robot in 3 Days demonstration, they use something that they call linear interpolation arcade drive, where they're looking at every value you put into your normal arcade drive function, like 1 and -1, and looking at the values between them and trying to predict really the best value for the drivetrain. In the end, none of this means anything until you have a good driver station. So on the top is just a picture I found online of a team who used a steering wheel to control their drivetrain, and it's actually what Team 971 used. It's very effective for turning. And the bottom is Team 254's alternative, where they have 2 joysticks set up in their Cheesy Drive systems. You would have the left joystick moving forward and backward, and the right joystick moving to the left and right to control direction. There's also a few other tricks you can use to control a drivetrain. Input squaring. This is the curve of y equals x squared, back to your high school algebra. Very fun, right? So, y equals x squared. So now, if I put in the x value of 0.2, so say my joystick is at 0.2, now my y value is not at 0.2, it's at like maybe, 0.05 or something. So now I can have finer control at lower extremities, and I still can go all the way up to full power if I'm at x equals 1. And if I want an even steeper curve, an even shallower curve, I could use the function y equals x cubed. So here, if you have x equals 0.2, y is an even smaller value, and you get a lot finer control of your drivetrain at smaller rates. WPilot also supports this. So there are 3 arguments that are supported in the tank drive function. So if I go over here, and I go to SI, the third argument, so the first 2 are what? The left side and the right side, right? We saw that earlier. The third one is whether you want the inputs to be squared. WPilot calls this squared inputs. So if I say false, I'm not going to square the inputs. I'm going to go just in a straight line. It's a linear relationship. So if I run that code concurrently with my other code, you can see the difference. So that's 1. And, fire up another shell. And if I go to so now it's another simulator. Let me just try to fit these into 2 screens. Yeah, I don't have a lot of space here, but you can kind of see the robots. They're lined up right now, right? And if I want to, so the top one is running non-squared inputs, I believe, and the bottom one is running squared inputs. And if I put in a step value of 0.5 for each of them, oh, no, I can't see that anymore. Put in a step value for each of them. and I run it in autonomous, so I'm just telling the robots to go straight right now, right? If I run it in autonomous, I'll go about that far in 3 steps and about that far in 3 steps, and you can kind of see that there's a little bit of difference in how far they've traveled. So it's very minute, like 0.5 squared root is just, what, 0.25, so you're not going to get much difference. But when you're going at a really high speed and you suddenly want to, say, line up to shoot a Frisbee, you need this input squaring. One more trick. Oh, okay. So this Drivetrain, which you saw earlier, has 2 rate 63R encoders on it, which means they just measure the rate at which the wheels are turning. So once that connects, I'm going to be able to show you some output from the encoders. So let me just fire up. Oh, I have to connect to the robot. That'll be helpful. So, go. And we'll watch that. Okay. Oops, sorry. This might take a bit. Connecting to the robot's a bit of an ordeal, but just give me a second. Anybody have any questions so far? Cool. All right. Yeah. So the program I'm currently running is a version of Dustin Spaguzza's Robot Pi. So they have a simulator and direct robot control. You can upload your codes to the robot, but like, let's say you're at home and you don't want to drive to school in the middle of the winter where it's freezing and it's snowing out and your robot's in a bathroom like we have it, and you don't want to go in there just to drive it. You can now just run the simulator and it'll control the robot in 2 dimensions. So yeah, that doesn't control the robot directly, but I could do that using Robot Pi. Yes. It's called, the simulator is just a part of Robot Pi. Where are we? Robot Pi. So far back. Yeah. They're trying to integrate simulators into C++ and Java. It's called Gazebo. They did a beta over the summer. We haven't heard back from that yet. So right now, just the simplest version is, oh, that would be helpful if I could get it on there, actually. Simplest version is Robot Pi. There you go. Get out of the way. Yeah, so that's the link that you can go to visit it and see what's going on. So let me just try to connect to the robot now. And I'm now on that. Okay. So here I am connected to this robot. And if I enable it, so have a look at the bottom input here. So I'm writing down the input from the output from the left encoder and the right encoder, which is the position that it detects. So now if I run the robot, now let's look at the outputs. Oh, sorry, I'm not running the code. That would be helpful. All right, so once that uploads, you're going to see we have 2 encoders just on the gearboxes, and you can see how fast the gearbox, how fast the motor is rotating, how fast the wheels are going, and as a result, you can control more accurately the robot. So that's just spitting out random values right now. Over the course of using encoders, there are a few other things. You have to make sure that your encoder interfaces nicely with your shafts. Teams have had problems in the past with your connection with the gearbox. So the recommended encoders that first uses are the US Digital V4P, which is developed with Benchmark, and the Gray Hill 63R, which Best Pro should be. Now I'm connected to the robot. Enable that. I now get values from the encoders. You can see there's a little bit of error right now, so let me just get back to the right. So left encoder, it's a little bit fiddly, but left encoder is reporting -3, right encoder is reporting 960. So So now if I move the right encoder, you can see I'm getting increasingly negative values. And in the opposite direction, I'm getting increasingly positive values. And the same applies to the left side. So going more negative and going more positive. So the encoder is just a sensor on there that detects how fast the motor is rotating. Let me get that into implementation. Oh dear. Okay. So I had encoders on there. The general method of control there is something that we can call open loop or closed loop control. So up to this point, what I've been telling you is just how to tell a robot what to do. The robot doesn't tell you anything in return. You're just giving the command to the robot. With an encoder, you can perform what's called closed loop control, which means the robot is giving you feedback. So now I can say, robot, move your right motor at 100%. Maybe the motor has a few issues and it only moves at 95%. Now the encoder will spit back that value to me, and I can tell the robot, you're not moving fast enough, give me 105%, and now it will move faster. So here's a graph of that type of control. It's called proportional integral derivative. You'll commonly hear it as PID. It's something that a lot of industrial automation uses. So this is, not necessarily a graph that we implemented, but KP is just how much we want to change the value every single time. So now you can see the wave's getting closer and closer to our ideal point, just this straight green line. And as we get closer and closer, we're getting output from the robot saying, I want you to move faster or slower. That, in essence, is how we make a robot go. So you're controlling the left side, the right side. You have all sorts of algorithms controlling it. And it really only takes 3 to 4 lines, right? So just to conclude that, I have sourced a lot of images from this presentation from Daniel Ernst from Team 469, Las Gorillas, Patrick Fairbank, and Dustin Skakuza for writing the Python libraries. Thank you very much. I'm NW Chen on GitHub and Chief Delphi, and that's my email. Thank you. Does anyone have any questions? Okay, just as a heads up. Yeah, sorry. Okay, so the question was, how do you make sure a robot goes straight 100% of the time? That's actually a really difficult problem that a lot of teams have tried to tackle. There's 2 primary methods of doing that. You can have a gyroscope on your robot, so just a device that measures the angle it's facing. And you might want to, let's say you want to go 0 degrees straight ahead. You just make sure that you're not going any deviation there. But that can be a little bit difficult because the gyroscope is, corrupted by things like the robot's vibration, electromagnetic interference. So what other teams might use is the encoders, which we just saw. So now, if I want to go straight, the motor should be outputting the same values, right? Which means the encoders should also be outputting the same values. If they're not, I'll just tell the encoder that's moving slower, move faster, or the encoder that's moving faster, move slower. So it's this sort of balance between the motor's error, any electrical issues you have. It's really impossible almost to go exactly straight. So it's actually a surprisingly difficult problem. And yeah. Yes.
How often that value is the robot?
Like the source of that error? So there's a few issues all the way to the motor. We didn't have an electrical presentation, but the basic way the control system works, for those of you who aren't familiar, is we have voltage from the 12-volt battery. It goes into a power distribution board, which gives it to all the motors and all the control things in the robot. And then you go through a speed controller, which is even more wires and some disconnects. And then you go to another wire, and then it goes to your sim. Every single step of the way, you have increased resistance in your circuit, which means your motor could be getting less voltage than you really wanted it to. So one of the things that teams do, aside from using encoders and everything, is something called CAN, which is the controller area network. So that's a built-in thing into the motor controller, a built-in resource that like cars use. They just put a cable in, it's kind of like a telephone cable, and it tells you how much voltage, how much current is going through the motor controller. So you can skip all the stuff in between and sort of directly get the voltage the motor's getting. But there's a lot of sources of error, aside from any discrepancies in your sim, like let's say you have a 6-year-old sim and it's full of grime and everything, and you don't know that. You could control it more effectively using CAN or encoders. Any other questions? Yeah. Yes. So I don't have an autonomous demonstration here. Autonomous is really where a lot of the creativity in first, I think, comes through. So what Team 254 has done in the past, which is fairly admirable, I can't show you right now, but they have a, actually I can show you. All right, let me run my thing. So you can all see what's on my desktop right now, but it doesn't matter. And it should be in research. And then, nope, not that one. Sorry. I have too many folders on my computer. So, oh yeah, another thing when you're coding, just document it well and don't be disorganized like me. Oh, I know where it is. It's very troublesome. Should we call that? Look at all the things. Oh, there we go. I saw it in there. Okay, let's run Hermite spline curves. So, there is a graph, not a graph, but like a portrait of points along a curve which is interpolated among 3 points. So let's say I want my robot to start at the white zone and then go to the low goal and then drive back and then go to the high goal. I can define those points on the field. So now this is an algorithm which, if I can get my nasty organization under control, is, there we go. Right. Too much code, all right. All the way over there. The heart of this code is these 3 equations, which are defining a path for the robot to go along. So now, if I can, too many tabs. There we go. Okay, so all those lines horizontally are the normal lines to that curve, and you can demonstrate the exact path the robot's taking. Another thing teams use, so normally you would just use like a time-based autonomous. So we have a sample here. And in this autonomous function, we say, let's say autonomous lasts 10 seconds. Every time, so if your timer is less than 2 seconds, drive this value. If you're above 2 seconds now, just stop. So the simplest and probably most common way of autonomous control is just time-based. So you want your robot to move for a certain amount of time. If you're a little more complex, you can tell it to respond to like sensors. So teams can use what's called a state machine to put the robot in a certain state. Like, I'm ready to shoot. Now I'm ready to drive to the local. Now I'm ready to drive back. So you get sensor feedback. There's a lot of things online. There's no way I could talk all about it. I don't even know all about it in one presentation. But it's a lot of complex robot control, and teams really approach it. It's 10 seconds of robot control only, or 15 seconds, but teams apply a lot of creativity and a lot of research into doing it. Yeah. In a week? Well, during build season, every day forever, and then and then off build season, we usually just do member training here. So we would it's a lot more simplified stuff, I guess. So I wouldn't really be doing much research, but like just casual browsing. If you wanted to know more about this, just like casual browsing on Chief Delphi's programming forum, looking up what other people have done. There's this guy Ether on Chief Delphi who posts really complex algorithms, and there's all this stuff that is unexplored. But a lot of people post their code on GitHub, so I was actually going to talk about that. I have all of our code here is in this URL. Everything in this demonstration is at github.com/steelhawks/makeitgo. It's on your papers. And a lot of teams put their code on here. So if we were to visit, world champions, right? Team 254. There are these really nice people who put all their code online because my Wi-Fi is not working. But oh, actually. Yeah, that's probably the reason. There we go. Okay, so a lot of teams put their code online, and it's a really good resource for you to learn from. So, if you wanted to do research in your spare time, you can just look through a professional team's code, like Team 254 or our code. We upload that. And please, no. Oh, yeah. And that applies to anything, right? There we go. Okay, so here's Team 254, their 2014 robot. All of this code, it's like, what, 283? So that's 283. A commit is an edit, and that's only the ones they've recorded, so they probably have a lot more. 8 people contributed to this code. It's a work of art, and they just published it online. So if you wanted to do more research, you could just go into their code and see what has Team 254 done. They've done this crazy stuff with, like, all these different things. They call it, what, cheesy drive helper. Chezzy robot, all these things which are highly complex, it's actually all available to you. And you can ask them on Chief Delphi or wherever just for research. Just message people. They're all very friendly, and look for code online. Mm-hmm. Yes. Yeah, I think so. So that's actually what I do. I have my MacBook here, and our team has 2 developer laptops which are identical. The utilities are all available online. It should come, at least directions are online or in the kit of parts, and they'll just tell you. So for Java, you download something called Sunspot FRC SDK, and it doesn't really change from year to year. But let's see. Nope, I'm in the wrong. How am I holding this? Nope, let's close that. It's yeah, software is generally similar to year to year. Like C++ uses something called Wind River is their development environment. Java is NetBeans now, it's Eclipse. So they give you the instructions for the software, you can install it. It's generally free, or they give you a license for it. And then if you wanted to set up a computer other than the classmate they give you, all the instructions are basically online. And if you had any trouble, you could always ask on Chief Delphi. Any other questions? Yes? Yeah. So I've been on this team for 3 years now, and every year I've tried to train a new number of programmers. I've made videos online for them and everything. There is no substitute for practice. So you got to write code on your own. If you can get a robot, just write code and upload it to the robot, figure out what's wrong. There are plenty of online resources. Like if you were to go on Chief Delphi and ask right now, how do I learn to program a robot? It turns out that there are actually a lot of posts just like that. Oh, look at all that. So if I go to search, and let's say, learn to program. What it'll be hit this thing. THHS. Okay, if I search for that, look at all these posts about how to help programmers, right? Well, not that one. All these resources are online. They're available to you. I think one of the main concerns is just how to navigate through the jungle of all the resources. And to that end, you can just reach out to people. So we're here. I have a GitHub account, like I showed you. I have my email available to you. So if you ever needed help with programming, you reach out to a local team. You can ask questions on Chief Delphi. Like plenty of people answer these questions. I've asked them a lot. So people ask about how do you control a robot with gamepads, or does the compressor turn on and off automatically? You can get that question answered in 5 minutes just by going on Chief Delphi. So you got to reach out, you got to be active and try to teach yourself sometimes. But the main thing is just practice, practice, practice. Yeah, so every year they update this. So it's Screen Steps Live. They have all this stuff on how to program. Like if I wanted to learn to program with Java, I would just go there and look at all this stuff. Yeah, installation instructions are here too. So if you wanted to add software to your computer, and you can write all this code. They tell you how to do everything. It links to even more stuff. So all these things are available to you on the Screen Steps website. And that's support for C++ and Java. Yeah. Any other questions? Okay. All of the code in this demonstration, again, is available on our GitHub. So go. You would have to, in order to run the simulator here, you have to download RobotPy, which is the URL I gave you. It's on your papers. It's like 2 commands. You just write pip install. It's on your papers. So you can just look at all this code, browse through it. Here's the simulator. Everything is on here if you want to refer to it. We keep all of our code that we used in previous years on here. So like the shifting drivetrain, the code for that is now in this repository. If you want to see how it drives, look in drivetrain.java. That's how it works. So nothing is hidden away from you. We keep all of our code to the public. If you need help, you can look at our code online. You can reach out to me and the rest of the team, Priscilla, and we will help you. Any other questions? Okay. Thank you very much, then. Oh, sorry. Oh, yeah. So my email, I'm active on Chief Delphi and GitHub, but I'll respond almost immediately to emails. So yeah, any communication channel works for me. Anyone else? All right. Thank you very much.
out today and visiting Steelhawks. Priscilla is our main programming mentor. We have an engineering program mentor over here in Lane. Parent program mentor over there is Lyndon. Lyndon. I thank you all for coming out from other teams and other parts of the city. But feel free to stick around a while, ask some questions to some people on the team. If you have further details, want to get some of the electrical aspects of it too. Feel free to not being run out of the at any time. So thank you very much.
No, you kill it. Stop.